this, and you can count the number of times I say, I don't know. All right, as far as I know, I am now recording. Yes, I am now recording. So integration, use substitution. This is should just come up as a PowerPoint. And your goal for this, I hate to scare you, but you should be thinking about doing these in your head. I know I called it the shortcut method, or I used some term with it. You guys really picked up on it last week. It's a reality that's coming down the road. Is there's a pretty reasonable, it's not an unreasonable expectation that you start doing some of these in your head. I'll tell you what, let me open this up. Take a shot, please, at number 1 and 2. All right. I'm going to give you like 1 minute on total. So let me see. I'm going to get my phone. I'm going to set it for 1 minute. Be right back. You get started. Here it is. Wait. Make it bigger. There. Oh, I know I didn't want to do that. You guys just get started. Don't wait for me to screw around with this stupid software. There. Now get started. I'm going to turn my, it's a little clunky going from pen mode to live. So I'm going to, there. All right, I'm going to go into pen mode now. Oh, I could have done that from here. Never mind. Slideshow. Play from start. I can go right to pen mode here. There we go. All right, the number one, the way you do this, I get to use yellow. This is 2x to the third plus 1 to the 6th over 6 plus c. All right. Now, if you're thinking, my God, how did he do that? Here's what you're looking for. Usually it's the most complicated thing that you're actually looking to integrate. And in this case, the most complicated thing is that 2x to the third plus 1 to the 5th. The way I'm going to integrate that is I'm going to use a power rule. So that thing, that 2x to the third plus 1, I'm going to take that thing to the 5th, and I want it to be that thing to the 6th over 6. All right. Now, in order to make it go, you've got to do a u substitution. And part of the u substitution is you have to have the derivative of that thing. I'm using the word thing a lot. Maybe that's what you should be counting today instead of my ums. So that thing has a derivative. Its derivative is 6x squared. Well, golly gee, there it is right there. There's 6x squared. When you integrate, that 6x squared goes away. I mean, everyone asks me, well, where's it go? Where's it go? Well, where's the dx go? Where's the integral symbol go? These are all byproducts of the action of integrating. And if you don't believe me, just do a u substitution. And you'll see when you switch out the dx in terms of du, if you've solved for dx, that 6x squared in the best case is going to go away. And so there you go. Try it. The next one, what I'm looking at is okay, I'm looking at a power rule. The thing, if you will, is down here, and I'm looking at that thing to the -1/2 power. All right. So let me, I am going to rewrite this one a little bit. We got 8x squared minus 4. And we've got 2x to the third minus 3x. That's to the -1/2. Okay, in order to make this go, what I need as far as a derivative goes is I need a 6x squared minus 3. What the hell did I do there? 6x squared minus 3. Oh, wow. This is a good one. If I factor out a 3, notice I've got 2x squared minus 1. There it is. Okay, this is one you probably got to do U substitution for. I see where we're going, because notice that if I factor out a 4 from here, I'm going to get a 2x squared minus 1. So there it is. Okay, let's do a legitimate U substitution on this guy. Let me erase. I'll try to be neater. For U substitution, we're going to get rid of the 2x to the third minus 3x, and the du dx is going to be 6x squared minus 3. That means that our du over 6x. Okay, that scroll at the bottom of the page in red is my U substitution. So green and purple doesn't go, but this is what I'm going to do. So here's what I've got. We've got the integral. Okay, this 8x squared minus 4. In the interest of time, I'm going to factor out a 4 right now. So this is 4 times 2x squared minus 1. Okay, then now this part right here is going to be u to the negative 1/2. And then finally, I got to get rid of the dx, which is this, which I'm going to write this as du over, let's factor a 3 out of that. So I've got 3 times 2x squared minus 1. Now, in order to integrate, we have to have all the variables have to be the same. We've got x's and u's right now, but notice that goes and that goes. And what we're left with is the integral of 4/3 u to the negative 1/2 du. And power rule that thing, it's going to be an ugly fraction that I'm not going to simplify. So we end up with 4/3 u to the 1/2 over 1/2 plus c. You've got to put it back in terms of x, and probably have to simplify that. Again, if that were a free response question, you would not, but there you go. All right, let's see if I can, that was a tricky one. I'm a little surprised. I should have maybe looked at these a little more carefully before putting that one to you. I'm in pen mode. I'm gonna get out of pen mode. Okay, it's glitching on me. What's going on here? Why won't it let me? Oh, good Lord. All right, let's just do this. Let's do 7 and 8. Forget the upper and lower bounds. I just want you guys to practice with U substitution. I think 7 is walk in the park easy. So that's the challenge to you. Is it walk in the park easy to you? Think about what it is. Timer set for 1 minute. Get them both done. All right, my timer just went off. Okay, the one at the top is walk in the park easy. The one at the bottom, it's not. That one probably you gotta write it out. what you want to see with number 7 is the integral of e to the x, or the integral of an exponential, especially an e-based exponential, is itself. The only thing you got to deal with is the any chain rule implications. And I see that the derivative of 3x is 3. I need to pay for that, though. I can't just throw a 3 and multiply something by 3, and it's going to change. So what I'll do is I'll divide by 3. So there we go. And the integral of this one is 1/3 e to the 3x plus c. And what about show your work? No, you don't have to show your work with this. I mean, if this were a free response question, chances are this is part of a larger set of things you have to do, and going from here to there would be fine. All right. Now, the second one is that's not a walk in the park. I did the u substitution for you. So we've got, let me rewrite this. We've got the integral of 1 over x, 1 over u to the second, and then our du is x du. And it does, there we go. It's going to be a power rule. We've got the 1 over x and the x cancel out. And this goes to the integral of u to the negative second du, and that's u to the negative. I don't say to the negative third. That's, you want to add 1, so it's x to u to the negative 1 over negative 1 plus c, which let me finish in a bright color here. So we end up with negative 1 over u, which u is the limit of x, plus c. And that is the answer to that. All right. And let's see, I'm gonna, if you would like, you may go through the PowerPoint, and I hope I can tear it down. Why can't I get rid of this? There, okay. If you'd like, you can open that, do it on your own. There's 4 pages. I wrote this in 2008. I found this one. The answer keys at school. They're doable. They're use substitutions. I wouldn't say they're walk in the park easy. That one is. Number 3 is. And number 4 is too. All right. If you have any questions, ask me about them. You message me or ask me in class, hopefully when we're together Wednesday. Okay. Second up, slope field, separable equations and separable differential equations. And there it is. And I'm worried about my ability to have any kind of coherent pen work on this. Just apologizing in advance. Okay, let's start off by making a slope field for this. All right, what you do with a good practice, we're going to make a slope field. I'm going to give you an example of Euler's approximation, and then get a particular solution. All right, so slope field for this is, there's no y involved, so all you have to do is pick some values of x and put tiny little linear equations at those values. So for dy dx at x equals 0, well, we've got 0 minus 1 over 2 is negative 1/2. So everywhere x is equal to 0, we've got negative 1/2 as a slope. So those are all locations where x is 0. All right? So now what you do is you just move around, and let me see if I can do this. I don't want to do too many of these because I don't have time. All right, how about dy dx at x equals 1? Well, that's going to be 1 minus 1 over 2 is going to be 0. So we're going to have slopes of 0 there. All right. I hope you can look at that differential equation. Imagine the integral is going to be a quadratic. I think we just found the vertex. How about dy dx at x equals 2? Well, that's going to be 2 minus 1 over 2 equals 1/2. So we've got a slope of 1/2. right there. All right, and I hope you can appreciate that as we go out to the right, the slopes are going to get more positive, and as we go to the left, they're going to get steeper, as in more negative, and that's going to be a slope field for differential equation. Pen mode. Okay, Euler's approximation. Okay, this is really a matter of organizing more than anything else. Write this down. Dy dx equals x minus 1 over 2. Okay. Everything else can go on this page. So let me get out, erase as much as I can. I'm looking at the clock. Oh man, this is gonna, I'm kind of concerned. It seemed like it was gonna go faster when I was having my coffee this morning. Okay, the key is setting this up, what you wanna do. And by the way, I was looking ahead, and this is actually a topic in an upcoming video. So the fact that you guys are doing it now, you've seen it now, I know that the workload is insane right now. What we're doing, I feel a little manic, but we're actually doing an investment because what's coming, I think there's a lot of things that we will have seen by the time they get there. So here's how you want to set up an Euler's approximation. You begin at a location where you are now, a certain x, y. And we have that right there. We are at 0, 1. Okay, the next thing that you need is you got to have the differential equation you're using, which for our case, I erased it, but it was x minus 1 over 2. So what you do is you put this ordered pair in, and since there's no y value in this, so we're only looking at 0 minus 1 over 2, so our dy dx at this point is negative 1/2. Okay, the next couple of items that you have is you've got to have a delta x and a delta y. Delta x, what we're looking at is changes in x and changes in y. These change, when we write it like this, dy dx, we're talking about the derivative, and it's an infinitesimally small amount of change in x and y. A measurable amount is represented with this little triangle, delta y over delta x. Right? They're the same thing. This one is just a lot tinier, okay? So we're doing an approximation. We're not doing the elegant dy dx. We're clunking around in measurable increments of x and y. So again, this is an approximation. So our delta x is given to us right there. Usually it's, actually forget what I said. I always use 0.1 as my delta x. So let me put that in, 0.1. And then our delta y, well, the way you get the delta y is multiply delta x on this side by the delta x on that side. Those cancel out. So basically you multiply this times that, and that's your delta y. So if this were negative 0.5, this would be negative 0.05. All right, and then the last thing you want in your column is you want your x plus delta x, and then your y plus delta y. So that is going to be, we started at 0 and x, and then we incrementally went a 0.1, so our new location is 0.1. And then our y plus delta y, we were at 1 originally, and we backed off by negative 0.05, so we're now at 0.95. Okay, and in the interest of time, I think I want to show you guys parts and partial fractions. What you would do is, and this is really mechanical now, we've got 0.1 and 0.95, and you just repeat the process. Plug this number into your differential equation. Your delta x is going to be 0.1. Whatever this value is times 0.1 is going to be your delta y, and then you 0.1 plus delta x, and then 0.95 plus delta y is going to be your next increment, and then you got to do that. You got to loop it around. All right. Okay, so, and then the final thing is a separable differential equation. Okay, what we're looking at this is this is an integration, this is an integral you actually can solve. Whether the way it was presented to you was dy dx is equal to x minus 1 over 2. All right. And what you do is you treat that dy dx as if it were a fraction. You multiply this side by dx, multiply that side by dx. Those cancel out, and you're set up. Just tack on the integral sign. All right. So the left side is just y equals, and then we've got 1/2 times x squared over 2 minus x plus c. And the last thing you got to do is use your initial condition. I think our initial condition was we had this, by the way, this is a general solution. We had an initial condition. It's going to tell us what that c is. Our initial condition was 0, 1. So what you do is you plug in zeros for the x's, you plug in 1 for the y, and I think this ends up being 1 equals 1/2, and then this is 0 minus 0 plus c. So the c ends up being equal to 1. So we can go from general solution to using initial condition, we get what's called the particular solution. And that is going to be y. Let me switch colors here. It's going to be y equals 1/2 x squared over 2 minus x plus 1. All right. Okay. Wow. You guys are going to have to stay through lunch. I'm sorry. Let's get rid of this. And next up is integration by parts. Okay. Here it is at the view. Spend too much time screwing around with that view. Oh, forget it. What I want you to see is this is the product rule. All right, u times v, u prime times the first times the, I think I have that written backwards. It doesn't matter. It's first times the derivative of the second plus the second times the derivative of the first. Okay. Well, what you do is you rearrange it so that you've got one of the parts of your partial of your integration by when you have your product rule, you've got these two parts right here. Okay, and you put one of them to the solve for, and then what you're doing is you're integrating everything. And this, wow, I am embarrassed at my explanation here. What happens is the derivative, the integral ends up going away. And if you're clever about what you choose, how you break this up, you end up with an easier integral than what you started with. And I think this might be one where let me show you an example here. Let me open up. So this is, we've got a lot more room. And this to be bigger. And while we're at it, get out of the way, my God. Okay, that looks really good. Okay. Okay, here's the way you want to think about this. When you're setting up for integration by parts, what you got to do is it's like you're stocking the shelves. What you need is you need a U and a DU, and then you need a V and a DV. And the challenge is figuring out which piece to pick. And what and from this original integral, the pieces that you're going to have to populate into this inventory is you're going to have to get the u and you're going to have to get the dv. That comes directly from this original integral. And I'm just going to tell you what to use for this one because I just want you to see the procedure. We're going to use x to be our u, and anything not the x is going to be our dv, which in this case would be, I'm sorry, that should be e to the x. That's a typo. E to the x dx. All right. So we've started the process of setting up our integration by parts. Now, the next thing we've got to do is we've got to calculate what is the derivative of x and what is the integral of that dv there. Well, the integral is easy, and e to the x is its own integral, so this is e to the x. And the derivative of x is 1 dx. I mean, I think in the past I would say u equals x, du dx equals 1. Well, then move that dx over, and there you go. Now, the way you want to set this up is you're going to have the u times the v minus the integral of v du. And we're going to populate this with the little inventory we created, the shelves that we built. So this is going to be, okay, the u is x, the v is e to the x minus the integral. Well, the v is e to the x, and the du is dx. Okay? And we went from something that we could not integrate right there, it's supposed to be a sad face, to something we can integrate. This becomes x e to the x minus e to the x plus c. All right, and that is the integral of that using what's called integration by parts. I feel like I'm on a roll, and that went pretty good, and I got time. I'm sorry, it's just, you're witnessing the stress that everybody has with this remote learning. All right, let's do the ln of x. And one of the things I will speak to is what is your, how did you choose the u? How did you choose the dv? I know that's an issue and we'll talk about it. I just want you to get used to the process right now. Trust me when I tell you what to use, okay? So first thing I want to do is set up the little shelving unit that's going to contain all of our inventory. We want a u and a du, and then we want a v and a dv. Okay, we're going to use this as our u. How would you integrate the ln of x? I know what the derivative of the ln of x is. The derivative is 1 over x. But what's the integral? What function's derivative gets you the ln of x? We never talked about that. The way you're going to get this is through integration of parts, and it's going to be 2 terms, and you'll see what we get done. So let's use ln of x as our u. And let's not get ahead of ourselves. Let's make sure we've completely used up everything in that integral. So we've got the ln of x. So we've got that part accounted for. The only thing we haven't accounted for is the dx. We'll put that over here with the dv. All right, so now what we've got to do is we've got to differentiate the ln of x. So that's going to get us that du is equal to 1 over x dx, right? And now we've got to integrate the dx, and that's going to be x. All right, and I could have spaced that a little bit better, but what we end up with is you want to have u times v minus the integral of v du. I swear, my handwriting, I take a lot of pride in having decent handwriting. All right, there's the table. God. All right, so let's plug in what we've got. We've got the u is the ln of x. The v is x minus the integral of v is x again, du. So we've got 1 over x dx, which the x and the dx cancel out. So really what we've got is we've got the Let me rewrite this first term. I'm going to write this as x times the ln of x minus the integral dx. And next step, this thing is just going to bide its time. There's nothing more we do with that x ln x. So we've got x times the ln of x minus x plus c. All right, and you should never trust anybody over 30. This is something I remember when I was a kid. Let's take the derivative of this thing. Okay, we would product rule. And by the way, the derivative quiz, we'll take that the next time we see each other, which I hope will be Wednesday. I'm going to count the best among the two that we took. You took the one last week, and we'll be taking one the next time we see each other. So anyway, the derivative, we got a product rule, x times the ln of x. So that would be x, the first, times the derivative of the second, plus the second, times the derivative of the first. Okay, that's the first term. Now we got to do the minus x. The derivative will be minus 1. And the derivative of our constant is plus 0. Okay. Want that completion. So what we've got is 1 plus the ln of x minus 1, which is the ln of x. All right. And not bad on the clock. I could do one more of these. All right, tangent inverse of x. Yeah, we can do that one. This is a squirrely one. Where's the top of the page? Oh my God. All right, let me give you the protocols for what you look for in choosing your U. There's a mnemonic called L-I-A-T-E. The first thing you choose okay, and we're assembling this thing that is a U and a DU and a V and a DV. Now the things that come from the integral are the U and then whatever isn't the U, which is the DV. And the challenge is, what do we pick for the U? Well, your protocol for choosing the U is the first thing you want to look for is a logarithm. That's the one we just did, it's a ln. The second thing you want to pick is an inverse trig function. Okay. The third thing, this is A stands for algebraic. Next it'd be trig, general signs and cosines and the like, and finally exponentials. That mnemonic LIATE should be your guide to tell you what to pick. So what we've got is we don't have many choices. Our U has got to be the tangent inverse of x, which means that our dv is going to be, we've got to use up everything in this integral here, and we've taken up the tangent inverse of x. Our dv is going to be dx, and now we've got to fill the inventory. Well, let's integrate dx, and that's just going to leave us with x. And let's differentiate the tangent inverse x, which is 1 over 1 plus x squared. All right, and what that's going to leave us with is our integration by parts is going to be u times v minus the integral of v du. And in our little table we've got, that means that tangent inverse of x, that quantity times x, minus the integral of v du. Okay, we've got an x over 1 plus x squared dx. And we started today by talking about doing U substitution in your head. And this is where it really benefits you, because what you're looking at, here's what I look at when I see to integrate this. I'm looking at a rule using natural logs to integrate. And I see this is the argument of that natural log, and I see I need a 2x. So I U sub So in order to do that u sub, I need a 2x, and I've only got an x. So what I do is I'm going to put a 2 in. I'm going to pay for it. I'm going to balance it with a 1/2. So in essence, I've multiplied the whole thing by 1. And what I end up with is minus 1/2 the ln of 1 plus x squared plus c. And I forgot the first part. We've got the x times the tangent inverse of x. And that is your integral. All right. Now, believe me, I am very sympathetic that if you are not really confident with your u substitution, you gotta build that little table. U equals this, du dx equals that. Solve for dx, and you will get there. This is being recorded, so please check to make sure that you can get to this destination. But your goal has to be starting to do basic u substitution, recognizing what is a basic u substitution candidate, and then executing it capably in your head. That's the goal you want to work towards. You guys don't review if you have times tables, you don't need to check your calculator for 6 times 3, right? And frankly, you shouldn't have to be reviewing to take basic derivatives either. And as we move forward in math, we got to think about, at least while we're in calculus, this should be at the front of your head as far as knowing how to do these u substitutions quickly. All right. I have about, oh my gosh, I'm not bad on the clock. It looks like I got 20 minutes to show you a little bit of partial fractions. Okay. Yeah, that's my compressor outside. The heat pump. It's right over my shoulder. There it is. It's done. Okay, this is partial fractions. This is really an algebra technique. And supposedly you guys had this in pre-calculus or maybe algebra 2. I'm going to doubt you did because we were shut down and my colleagues were doing what they could to give you as much information as they could under unprecedented circumstances. So I doubt you did these. So we're going to sort of, this is, again, what my point is, this is more of an algebra technique than it is calculus. If we can do all three, we'll try to do them. I want to do what I think is a very basic one right now. Okay. First of all, you've got what it looks like a very elegant little integral. How do you integrate that? I guarantee you, if you try to do a u substitution, you're going to run into a dead end. It's really close to inverse tangent, but it's not that darn negative sign between the x squared and the minus 1. This is a candidate for what's called partial fractions. And so the analogy is like this. If we have like 5 sixths, and that's equal to something over 3 plus something over 2, right? Well, what are those numbers? That's kind of the analogy of what we're doing with partial fractions. What you have to do is you have to be able to factor the denominator. Notice we can do that. That's equal to x plus 1 times x minus 1. Right? So somewhere out there, could you imagine that there's a fraction that is something over x plus 1 plus something else over x minus 1? What are those a's and b's? Well, if we were to combine the, as if we were going to add these, if we were going to combine these two, we'd have to get common denominators. And what we would do is we would multiply everything by, well, we'd multiply the a by x minus 1 over x minus 1. We'd multiply the b times x plus 1 over x plus 1. And we would have, then everything would have the same denominator. Well, our analysis is going to focus just on the numerator. So we've got 1 equals a times x minus 1 plus b times x plus 1. Okay, now we're going to do a little what if game in order to find out the values of A and B. Maybe it's not what if. How about this? It's let x equal 1. Well, in this equation, when x equals 1, we've got 1 equals A times 0 plus B times 1 plus 1 is 2. So in this little equation, we've determined that B equals 1/2. Right? Now we need to find a value for A, so we got to find a value of A that will get rid of B. Well, notice B is multiplied by x plus 1, so let's let x equal -1. Okay, well, we've got 1 equals A, and then -1 minus 1 is -2 plus B times 0. And what we've got is now A equals -1/2. Does that work? Well, again, I said never trust anyone over 30. Does it work? Negative 1/2 over x plus 1 plus 1/2 over x minus 1. Let's do x minus 1 over x minus 1. And then for the b term, same thing. We're just going to add these up. X plus 1 over x plus 1. You don't have to ever do this again. This is just convincing you that this actually works. Notice in our numerator, we've now got -1/2 x plus 1/2 plus 1/2 x plus 1/2. And in the denominator, we've got x plus 1 times x minus 1. Simplifying the numerator, notice that this -1/2 x and that positive 1/2 x cancel out. And sure enough, we do end up with 1 over x plus 1 times x minus 1. Okay, so I hope I've convinced you that we have successfully broken apart that fraction 1 over x squared minus 1. And what that does is it allows us to have a relatively easy integral. And so we haven't done any calculus yet. So where we go with this is this integral of 1 over x squared minus 1 dx. We've now broken it apart with what's called partial fraction decomposition, I think is the technical word. We've got the integral of -1/2 over x plus 1 plus positive 1/2 over x minus 1, and that's dx. And by the way, it doesn't matter whether you put the a over, as long as you keep them straight. Like if you had done a over x minus 1 plus b over x plus 1, it would have come out this, as long as you didn't make a computational or algebraic error. It's not a matter of picking the right a and b to go over the right denominator. So anyway, hopefully you recognize that this is a natural log integral. The first term is going to be -1/2 times the ln of x plus 1. Then the second term is going to be plus 1/2 the ln of x minus 1 plus c. And yes, you do wrap up those natural logs in an absolute value. And chances are that's not going to be the simplified form. Let me take you to how a lot of the multiple choice questions might be written for this. It's a little easier to see if I rearrange this. So let me write it as 1/2 the ln of x minus 1 minus 1/2 the ln of x plus 1 plus c. And there's a property of logarithms such that if you have the ln of a minus the ln of b, that's equal to the ln of a over b. And while we're at it, if you had the ln of a plus the ln of b, that's equal to the ln of a times b. And it works for any base of logarithms, base 10, base 7. I default to the natural log. It's like exponents. If you had a x to the 5th time, if you had an x to the, oh, never mind, I'm belaboring the point. The bottom line, to simplify this thing, notice since we've got a factor of 1/2, we could write this as 1/2 times, well, ln of x minus 1 minus the ln of x plus 1 could be rewritten as the ln of x minus 1 over x plus 1 plus c. And when you're doing multiple choice questions, I don't remember offhand the topic questions that are coming up, but if you have a multiple choice question, chances are they're not going to leave it. They may not. I don't think they'll leave it like that. So what you have to do is you have to put on your detective's cap and see if you can get to one of the choices they do have. All right. All right. I'm looking at the clock. I got 10 minutes. In for a penny, in for a pound. Let's do another one. Okay, what you're looking for is first thing you probably want to look for is, does it use substitution work? Is this a candidate for long division? Is it one of the inverse trig functions? The fact that I'm doing this in the context of showing you guys partial fractions probably makes you think, nah, it's not going to work for any of those. And you're right, it doesn't. So make sure I get my space cleared out. So factor that denominator. I hope you guys are seeing x and x. And I'm thinking minus 5 plus 3. Is that it? Yeah. So what we've got, and I could write the integral dx. Let's just work on the integrand. Let's work on the fraction part. We've got x minus 2 over x minus 5 times x plus 3. And in some world, there is some value of a over x minus 5 minus x minus 5 plus some value of b over x plus 3 that will get us x minus 2 over that. So what we're going to do is we're going to write these so that they are in a form of common denominators. I'm going to multiply the a over x minus 5 times x plus 3 over x plus 3. Did that make sense? As I say this, sometimes I talk and my words are going and I listen to myself while I'm talking and it doesn't make sense. Here's what I mean. For the b, I've got a little room over here. X minus 5 over x minus 5. And for the a side, I'm doing x plus 3 over x plus 3. Sorry, that looks like a serial killer right there. It's tough, my hand is floating. There we go. Now that we've got that out of the way, let's just rewrite the numerator part of this equation. We've got x minus 2 equals a times x plus 3 plus b times x minus 5. And now we're going to select values that are going to make either a or b go to 0. So if I want a to go to 0, we're going to have to let x equal negative 3. So let x equal negative 3. What do you got? Well, negative 3 minus 2, we've got negative 5 equals a times 0, which is that's how we designed it, plus b times negative 3 minus 5 is negative 8. So b is equal to 5/8, right? So now we got to find a way to get rid of the b. So we'll let x equal 5. So 5, now we're putting this into, again, now we're applying that into this equation here. So 5 minus 2 is 3 equals, a is equal to 5 plus 3, which is 8, plus b is equal to 5 minus 5, which is 0, which leaves us with a is equal to 3/8. And unless I made a mistake, and it's possible, guys, forgive me, you have this on tape and all my errors are sadly revealed. What we end up with is we have taken this integral right here, and through partial fraction decomposition, we can now write this as the integral. Okay, what's a? A is 3/8 over x minus 5, plus, and then b is 5/8 over x plus 3 dx. And that's a pretty straightforward natural log integral. All right. Let me cut to the last one real quick. Something about that, my spider sense says I made a typo somewhere. I don't know whether you guys aren't telling me or what, but maybe it's right. I don't know. I don't have an answer key on me. Sorry. I'm going to do this one just because it's a situation I want you to have at least seen. We've got this. How would you factor that denominator? Well, hopefully you're seeing we can pull an x out of there. So we've got x times x squared plus 3x plus 2. And that factors, so we've got x times x plus 1 times x plus 2. All right, so what you do is you will set this 2 over that, x times x plus 1 times x plus 2. Okay, we're going to do a over x plus b over x plus 1 plus c over, is that a 1? Did I really say 1 but write 3? X plus 1 plus c over x plus 2. All right, unless I did something else that was stupid. That looks like we're set up. So again, let me just cut right to the how you get the a's and the b's that you got to analyze with this equation. 2 equals, okay, now again, we're going back to, if we wanted to add this fraction and that fraction and the third fraction, we got to get common denominators. So I'd actually have to take that a fraction. It's already over x. I need to multiply by x plus 1 times x plus 2. And then I'd have to take the b fraction, which already has an x plus 1 in the denominator, so it only needs an x and an x plus 2. And then finally the c fraction, again, which already has the x plus 2 in the denominator, so it just needs an x and an x plus 1. And when I said, okay, well, notice that each one of those a, b, and c coefficients, they each have 2 of the 3 denominator factors in them. So if I do let x equal 0, we're going to have 2 is equal to a times 1 times 2 plus b times, there's a 0, times 2, it doesn't matter what that is. And then we've got c times 0 times 1. So these guys go away, and what we're left with is that a equals 1. Okay, to get rid of, let's see, what if we use x equals -1? We want to be clever about choosing values of x that get rid of 2 of the 3 terms. So when we use x equals -1, we've got 2 equals a times 0 times 1. That one's gone. Plus b times -1 times 1. Okay. And then plus c times -1 times 0. And there we go. We got b is equal to -2. And then finally for c, I'm going to use x equals, what happens when x equals -2? 2 equals a times -1 times 0. Excellent. Plus b times -2 times 0. Okay, we're good. And plus c times -2 times -1. So I'm reading that c is equal to 1. And notice how little calculus is involved in here. Most of what we're doing is, got 1 minute left. Most of it is algebra. And again, this is a technique called partial fraction decomposition. I see the clock. I'm very aware you guys are getting your full dollar value of calculus education. So we end up with 1 over x plus -2 over x plus 1 plus 1 over x plus 2, which that's an easy ln of x minus 2 ln of x plus 1 plus 1 times the ln of x plus 2 plus c. And there you go. All right. Hey, you are invited to attend tomorrow's Zoom class if you want to see that. I'll probably go and pick different questions so that you might have some variety, but otherwise, let me get out of here so you guys can get about your snow shoveling. All right. So thanks for hanging in there, everybody. Be well. See you Wednesday.